The next problem that we are going to take is 2-32 of our book. It says that a plane wall. So as soon as you see the word plane wall, that would refer to Cartesian coordinates. So these are different words that you need to look at very carefully while you are solving any problem. It says a plane wall means we would be dealing with Cartesian coordinate system. A plane wall of thickness 2L is equal to 40 millimeters. So this is the thickness of the wall. This whole thickness is 2L is equal to 40 millimeters. And thermal conductivity 5 watts per meter Kelvin. As soon as you are told that thermal conductivity is 5, you are also being told that the material is isotropic. Otherwise the conductivity would then be a function of X or Y or Z. So right now conductivity is constant, so therefore we are having constant properties, means that the material is isotropic, and K would be taken out of the differential sign. So this wall experiences uniform volumetric heat generation. This wall experiences uniform volumetric heat generation, means there is Q dot at a rate of Q dot. So Q dot is there. While convection heat transfer occurs at both of its faces at x is equal to minus n and plus L. Now it means that this face is at minus L, as you can see over here, and this face is at plus L, not the edge, rather the whole face. So if you have a wall at your home, so the inner face of the wall which is inside the room, and then the outer face of the wall which is outside of the room. We are talking about the whole face. And so the outer face is at x is equal to plus L. So from minus L to plus L, the length of this wall, or rather the thickness of this wall, would be 2L, which was given to us as 40 millimeters. So while convection heat transfer occurs at both of its surfaces, so from here convection is taking place, it means that there would be a fluid over there, because convection will take place when a fluid flows over a wall or a surface, and there would be a fluid on this side as well. So each of which is exposed to a fluid of temperature 20 degrees Celsius. So on both sides we have a fluid which is at 20 degrees Celsius. So it means that we are given T infinity as 20 degrees Celsius, free stream temperature. Under steady state conditions, so as soon as you see the word under steady state conditions, it means that dava T by dava T would be 0. So under steady state conditions, the temperature distribution in the wall is of the form A plus Bx plus Cx square. See, if there had been no internal heat generation, considering the one-dimensional heat transfer and constant properties, and under steady state conditions, this temperature distribution would then had been of the form A plus Bx, if you recall what we had covered in the lecture. But since there is internal heat generation, the temperature distribution will no more be linear, so therefore it is A plus Bx plus Cx square, where A is 82 and the units of A would be the same as those of T, 82 degrees Celsius. B is minus 210, but the units of B, see, the units of B multiplied by X would be the same as the units of temperature, means Celsius. So therefore B would have units of degrees Celsius per meter, and C would have units of degrees Celsius per square meter, because degrees Celsius per square meter multiplied by x square means multiplied by square meter will give us degrees Celsius. So the value of C is minus 2 exponent 4 degrees Celsius per square meter, where x is in meters. The origin of the x coordinate is at the midplane of the wall. This is what we have already figured out. The origin of the x coordinate is at the midplane of the wall. So this is the place where x is 0. Only then this can be at x is equal to minus L, and this can be at x is equal to plus L. There are several parts. The first part says that sketch temperature distribution. Sketch temperature distribution means we need to sketch the curve which is a plus bx plus cx square, and then it says what is the volumetric rate of heat generation q dot in the wall. In part C we have to determine the heat fluxes at the two faces, and part D says what are the convection coefficients at the two surfaces. So let's take each of those parts one by one. The first part is sketch temperature distribution. So all we need to do is use that temperature distribution which is a plus bx plus cx square and put different values of x to find out the value of temperatures at different points. For example, logically we may find out temperature at the mid plane of the wall at x equal to 0, at x equal to minus L means at x equal to minus 20 millimeters, and at the other phase which is at x equal to plus L means at x equal to plus 20 millimeters. So if we put x as 0 in a plus bx plus cx square, we get temperature as A, and A is what? 82. So we will get temperature as 82 degrees Celsius where x is 0. Similarly, where x is minus L means where x is minus 20 millimeters means 0.02 meters. So if in a plus bx plus cx square we are given A, B and C, and if we put x as minus 0.02 meters, we get temperature as 78.2. And similarly at x equal to plus L means at x equal to plus 20 millimeters, we get the temperature as 69.8. So 78 to 82 and then to 69.8. 78 to 82 and then to 69.8 degrees Celsius. So this is the temperature distribution, and it would kindly do not join it with a straight line because the distribution is a plus bx plus cx square, which is quadratic. You can put some more values. You can find out temperatures at, for example, minus 10 millimeters and plus 10 millimeters. So the more points you put in there, more accurate would the curve be. Now in the second part we have to find out the volumetric rate of heat generation in the wall. So where is q dot? In the first four equations, q dot is not there in the Fourier's law of heat conduction or convection or radiation, but it is there in the heat diffusion equation. So we would be starting with the heat diffusion equation in Cartesian coordinate system, means dou by dou x of k dou t by dou x plus the same thing in y plus the same thing in z plus q dot is rho c dou t by dou t. Now since we are given that temperature is a function of x only, T is a plus bx plus cx square, so therefore y and z will get cancelled out. Therefore y and z will get cancelled out because T is a function of x only. So it means that the case is of one dimensional heat transfer, and we are also told that under steady state conditions it means that dou t by dou t would also be 0. So therefore q dot would be dou by dou x of k dou t by dou x, and since we are also told that k is 5, it means that k is constant, so therefore k will be taken out of the differential sign and it would be second derivative of temperature with x. So the first derivative will give us b plus 2cx, and if we differentiate it again we get 2c, and if we put the values of k and c which are provided, we get 2 exponent 5 watts per cubic meter, because the units of q dot is, if you recall, q dot was heat generated per unit of volume, therefore the units would be heat generated means watts per unit volume means per cubic meter. Then in the third part it asks us to find out the heat fluxes at the two faces, means what is the heat transfer per unit area over here and what is the heat transfer per unit area over here. Now as seen, this phase is at a temperature of 78, this phase is at 78, and this phase is at 69, and this phase which is at 78 is facing a fluid which is at 20. So what will happen is that the heat will flow outwardly, and this phase is at 79, and which is being surrounded by a fluid at 20, so the heat will also come out of this phase. So from the two phases heat would be coming out, and there is a fluid flowing over on both the faces, which would make it the case of convection. So one way is that we can find out the heat flux. Heat flux is nothing but the heat transfer per unit area. So we can find out the heat transfer using HA delta T, but the thing is that we do not know H. So we would not be able to find out the value of the heat flux unless we come to know the convection coefficient, and we have to find out the convection coefficient in the next part, in part D. So right now we would not be able to apply Q is equal to HA delta T. So what we would be using is the Fourier's law of heat conduction. Why we will use the Fourier's law of heat conduction? The reason being that we will say that whatever heat is conducted till this phase, will be further transferred via convection to the fluid. The two values of the heat transfer would remain the same. Why? Because the system is under steady state conditions. So when the system is under steady state conditions, the heat transfer from point A to B would be the same as the heat transfer from point B to C and onwards. So the heat that will be conducted from that point of energy generation till this phase would be the same amount that will be convected further, that will be transferred further via convection. So we would be making use of minus Ka delta T over delta X, or rather dou T by dou X, or dt by dx. So we would be finding out the heat fluxes using minus Ka dt by dx. Why dt by dx? Because temperature is only a function of x. It is not a function of y, it is not a function of z, and it is not a function of time. So therefore the heat flux would be minus K dt by dx, and dt by dx would be B plus 2Cx. Now we have to find out the heat fluxes at the two phases, at minus 20 millimeters and at plus 20 millimeters. So all we need to do, we are given the values of B and C, all we need to do is put X as minus 20 millimeters after converting it into meters, and then secondly put X as plus 20 millimeters. So we will get the heat fluxes at the two phases, at this phase and at the other phase. Now if we put X as minus 0.020 meters, we get the heat flux as minus 2950 watts per square meter. And when we put X as plus L, means plus 20 millimeters plus 0.020 meters, we get the heat flux as 5050 watts per square meter. So kindly note that one flux is negative whereas the other flux is positive. Why it is so? Because the heat is flowing in this direction. So the heat is flowing in negative x-axis direction, so therefore the heat flux is negative, minus 2950. Minus sign is only telling us that the heat is flowing in negative x-axis direction, nothing more than that. And the other heat flux is 5050, that is due to the reason that the heat is flowing in positive x-axis direction, so therefore it has a positive sign. Now then in the next part D, we have to find out the convection coefficients. So for convection coefficients we would be using HA delta T. So now and if we take this area into the denominator of Q and call it heat flux, so now we know the heat flux. At this phase, at the left phase, the heat flux is 2950. You can call it minus 2950, but minus sign is only telling us the direction. The magnitude of that heat flux is 2950, and on the other phase the heat flux is 5050. So we know the heat flux, we know Ts. At this phase the value of Ts is 78, and at this phase the value of Ts is 69. So kindly note that we do not have 78 at this point, rather the 78 is the value of temperature at this whole face. For example, if this is the inner surface of your house wall, so the whole inner surface is at 72, and similarly the whole outer surface would be at 69. This is what it means. So we know the values of Ts in both the cases, and T infinity remains 20 degrees Celsius. So the only unknown in this equation is H. So we would easily get H using this equation. So if we first put the first heat flux at this phase, which is at minus 20 millimeters, the value of which is 2950 watts per square meter, Ts is 78.2 and T infinity is 20, we get H at x is equal to minus L, or at x is equal to minus 20 millimeters, as 50.6 watt per meter square Kelvin. The units of convective heat transfer coefficient are watts per meter square Kelvin. And for the second case, for the second phase, for the other phase, we get the convective heat transfer coefficient as 101.4 watts per square meter Kelvin. So these are the first four parts that we have solved. Now in the next part, if I go back, in the next part, E, it says obtain an expression for the heat flux distribution. Heat flux distribution means, see, what does temperature distribution means? It means T as a function of x. So what would the heat flux distribution mean? It would mean heat flux Q double dash as a function of x. And then it says, is the heat flux zero at any location? So we have to find out the heat flux distribution, and then we have to find out the location, means x, where the heat flux is zero. If you notice, we have already found out the heat flux distribution. Where it is? Here it is. The heat flux is minus k times B plus 2Cx. It is heat flux as a function of x. So this is what we have already found out. Now we need to find out the location where this heat flux is zero. They are asking that, is there any location where this heat flux is zero? So if we are to find out that is the heat flux zero at any location, all we will do is that we will equate this heat flux to zero. We will equate minus k times B plus 2Cx to 0. K is 5, B is given, C is given. So x is minus B over 2C. X would be minus, because 0 upon k would become 0. The value of k is 5. So we will be left with B plus 2Cx as 0. And when B plus 2Cx is 0, so therefore x would be equal to minus B upon 2C. And if you put the values of B and C, we get minus 5.25 exponent minus 3. And since it is x, the value is minus 5.25 exponent minus 3, but the units would be those of length, means meter. Means x is minus 5.25 millimeters. So this is the value of x. This is the value of x. This is that value of x where heat flux is 0. Now what does this mean? How can heat flux be 0? You need to think over it. How can or where can heat flux be 0? Heat flux would be 0 where there would not be any heat flowing through that point onto the other side, right? So if we take a look at this curve again, where this value of temperature was 69, and then over here we had 82, and over here we had 79.8. So if we draw a line where x is minus 5.25 millimeters, so this is the point where x is minus 5.25 millimeters. So this is the location, this is the section where heat flux is in fact 0. It means that no heat will pass through this point in this direction or in this direction. This will not happen. So what does this further mean? See, this heat flux is 0 would mean that the medium of energy generation is placed at this location. See, there was a Q dot in this particular wall. Probably, and we were not told its location. We were not told where it has been placed. Probably some of you might be thinking that it was placed in the middle, but it was a wrong presumption, because we were not told that it was placed in the middle. And if you notice that if that energy generation wire or whatever that material is, if that had been placed at the middle, then the temperatures at the two walls would then had been the same. Why? Because T infinity was 20 degrees Celsius on both sides. See, when we started solving the problem and the temperatures at the two faces came out to be different despite having T infinity the same 20 degrees Celsius on both sides, that was the first indication. That was the very first indication that the medium of heat generation is not placed at the middle, since the curve was not symmetric. So x is equal to minus 5.25 millimeter is that place where heat flux is 0. It means that heat is being generated from this section and is then moving in both the directions. That is the only way that the heat flux can be 0. It means that heat flux is not crossing this point. Rather, from this point it is moving in both the directions, negative x-axis and positive x-axis. This is what it means. This is the importance of this part E. And if the heat flux is 0 over there, that would also mean that the temperature is maximum. So that would be the point of maxima. See, when we have, we had put, kindly note that we had put this heat flux which is minus k dt by dx as equal to 0. So minus k went into the denominator of 0 and became 0. So what were we left with? Dt by dx is equal to 0. So when is dy by dx equal to 0? From your intermediate knowledge of mathematics, where is dy by dx is equal to 0? That would make it the case of maxima or minima, right? So therefore if dt by dx is 0 at minus 5.25 millimeters, that would make it the case of maxima or minima. And in fact this would be the case of maxima, because if you put this second derivative you can find that out. So it means that the temperature is not maximum at the midpoint 82 degrees Celsius. It is not. Rather, the maximum temperature would be at minus 5.25 millimeters. And the curve would then be adjusted in this manner. The curve would then be adjusted in this manner as I have shown from red curve. And you can find that value out. I have not found this value out, but I should have, but you can always find that value of temperature out. All you need to do is put minus 5.25 millimeters and in a plus bx plus cx square, and as far as I remember the value of temperature at this point was 82.5 degrees Celsius, but you can always find it out. It would be a temperature greater than 82. Now in the next part, in the last part, it says that if the source of the heat generation is suddenly deactivated. What does this mean? If the source of heat generation is suddenly deactivated, it means that if we make the q dot equal to 0, means that if it is a wire carrying current, so if we let the current stop flowing, then what is the rate of change of energy stored in the walls at this instant? So what will happen if the heat generation is deactivated, if it is stopped? Of course the temperature would start going down at every section. For example, the temperature at this face was like 78, so it will start coming down from 78 to 77 to 75, and after some period of time it will become in thermal equilibrium with the fluid 20 degrees Celsius. The same thing will happen over here. The temperature over here was 69. So if that source is deactivated, if that source of energy generation is deactivated, then the temperature would start coming down from 69 to 68 to 67, 66, 65, and eventually it will attain thermal equilibrium with the surrounding fluid, which is at 20 degrees Celsius. So we have to find out the rate of change of energy stored at this instant, means initial rate of change of energy stored. Kindly note that it will be energy storage in negative terms because the heat will start going out of this wall. So the rate of energy stored over here is the negative rate of change of energy storage, because the heat would be going out and not come in. So we would be starting with the the heat diffusion equation, because that is the only equation which gives us the rate of change of energy stored. Dava T by dava T, rho C dava T by dava T. See, dava T by dava T is something else, and rho C dava T by dava T is something else. Dava T by dava T is the time rate of temperature change. So over here we are not being asked to find out the time rate of temperature change. We are being asked to find out the rate of change of energy stored, means this whole term, rho C dava T by dava T, the rate of change of energy stored in the wall. So writing the usual equation of heat diffusion equation in Cartesian coordinate system. So the second term will get cancelled out and the third term will also get cancelled out. Why? Because T is a function of x only. It is a one-dimensional heat transfer case, and we have deactivated the source. So therefore Q dot will also vanish now. So therefore rho C dava T by dava T would be k times second derivative of temperature with x. Would be k times second derivative of temperature with x, and if we derivate temperature with x for the first time, we get b plus 2cx, and upon differentiating it in the second time we get 2c, because the differential of b with x would be 0. Now if you put the values, we get minus 2 exponent 5 watts per cubic meter. So minus 2 exponent 5 is the, see, we have got a negative sign. It shows that the energy is in fact going out of this wall. So this is negative energy storage. Minus 2 energy is going out at a rate of 2 exponent 5 watts.